Linear independence. This is an adjective that describes a list of vectors that ends up playing a really important role in a lot of the theory of linear algebra. Now, before we define what this important term means, I actually want to define what the opposite of the term means. And this is the notion of linear dependence. So what does this mean? We call a list of vectors, so I'm calling this list of vectors L, and the list of vectors is labeled v1, v2, up to vn. We call this list of vectors linearly dependent if it is possible to find a linear combination of that list of vectors that equals 0, where at least one of the scalars used in the linear combination is not equal to 0. So if you can produce the 0 vector with a linear combination where at least one of the scalars you use in the linear combination is not 0, automatically you know that the list of vectors you're dealing with is called linearly dependent. Let's look at an example to illustrate this concept. So here, what we're doing is we're taking a particular linear combination of 4 vectors in R3, and this linear combination produces the 0 vector. Right away, we know that this list of vectors must be linearly dependent because at least one of the scalars we use in the linear combination is 0. In fact, or is not 0. In fact, 3 of the 4 scalars we use are not 0. Now, I want to point out that we can more elegantly write this equation as a matrix vector product. That's the point of matrix vector products, is to better present, or matrix vector products give us a tool to better work with linear combinations. So the first vector in our list was 0, 3, negative 1, and that's the first column of the matrix we're going to use here. The second vector was 0, negative 2, negative 1, which is the second column, and then negative 5, 1, negative 2, and 0, 0, negative 2 are our last 2 columns. The scalars we used in the linear combination were 4, 6, 0, and negative 5, and that's the vector we're multiplying our matrix by, and what we found was that this particular linear combination produced the 0 vector. So we can sort of visualize all that data here. We have the columns of this matrix we're creating, which are given by the vectors that we originally started with. So that's the list of vectors we're interested in here. We scaled each of those vectors by numbers, which can be organized into this vector we're multiplying our matrix by. And then when we took this linear combination, we produced the 0 vector. The punchline here is that the matrix we just created, A, has linearly dependent columns. And the way that we are verifying this is by noting that the vector 4, 6, 0, negative 5 is in the null space of this matrix. When we multiplied this matrix and multiplied by this vector, we produced the 0 vector. And the interesting thing about the vector we're multiplying by here is that at least one of the coordinates is not equal to 0. And in fact, here, 3 of the 4 coordinates are not equal to 0. Here's another example of a linearly dependent list of vectors. The reason I know this list is linearly dependent is because someone is handing me this equation. When I take the first vector on the list and scale by 2, and then the second vector on the list and scale by negative 3, and then the third vector on the list and scale by 5, and add everything up, I produce the 0 vector. At least one of the scalars used here is not equal to 0, and in fact all 3 are not equal to 0 here, which means this list of vectors is linearly dependent. Now, I think it's kind of interesting that we can view this equation geometrically. So what we're saying is that 2 times the first vector minus 3 times the second vector plus 5 times the third vector is the 0 vector. So let's imagine, so we have this diagram of vectors here. If we start in the upper left-hand corner and we just follow a pathway, what we're doing is we're geometrically interpreting this equation. We're going through 2 times the first vector in my list, minus 3 times the second vector in my list, and then plus 5 times the third vector. And the idea is that when I go through that path, my start point is the same as my end point, which really means that I have had no displacement, which means I'm representing the 0 vector here. And sort of you can see how the relations work here. The first vector on my list I'm calling v1, and 2 times v1 is really just that vector scaled by 2. The second vector on my list I'm calling v2, And if I scale that by 3, I get the this sort of vector in green down here. And then the third vector on my list I'm calling v3. And when I scale that by 5, I get back to where I started. So we have this sort of diagram which illustrates geometrically how these 3 vectors depend on one another. So the algebraic definition says your list of vectors is linearly dependent if you can produce the 0 vector with a linear combination where at least one of the scalars is not 0. And here we have a diagram representing that geometrically.